All right. Well, good morning, everybody. Thank you for the introduction, Lou, and the opportunity to be here. To all of you guys for joining. My name is Stokes. I'm going to talk a little about what makes South Carolina interesting, part of the Central and Eastern United States seismic design protocol. First off, I do work at HDR. We are a 12,000 person international company. Lots of different business groups that we are proud to represent, including several different places that we do have. Some people think of us as the #1 company in bridges. That maybe get some debate on other people on that, but I like to think that we do a good job of that. Just some examples of what we do, including a strange-looking person in the right corner of the screen right now, representing when we did some community outreach events, part of what we do. So today I'm going to talk a little about, like I mentioned before, what makes South Carolina interesting, some of the things that in the structural design elements that we have to consider, and then some of the places where we need to consider future study and further investigation. First off, South Carolina is indeed a seismic state. Lee Marsh mentioned a little while ago that South Carolina has had a pretty significant seismic event in its past history. 7.3 magnitude event in August of 1886. Killed approximately 100 people and is still the largest seismic event on the East Coast. Liquefaction was evidenced by some of these sand blows that you see shown in the right side picture. You can see those all up and down the coastal areas of South Carolina, indicating the breadth of the impact. So a little bit more. There's a coastal plain on South Carolina that impacts our seismology. A little bit like Dr. Huff just mentioned, we've got a kilometer deep in certain places, and so it makes it difficult for the USGS maps to be appropriate for our state. And as such, South Carolina actually has its own state-specific hazard map that is developed in response to this. Where I live in Columbia, South Carolina, is right around the fall line, which differentiates that coastal plain from the rest of our state. Once you get above that, you've got rock, and you've got much less seismicity, as well as a little bit easier ability to define the hazard. So these are some of the faults that we've got in South Carolina that are causing some of the seismic hazards in our state, as well as locations where we expect some of the higher shaking. And just as an interesting point, in South Carolina, of course, we don't just have earthquakes, we have hurricanes too. So as part of the challenge for being a South Carolina seismic engineer is designing a bridge that is both flexible enough for a seismic event, but also strong enough for a high wind event. So, South Carolina is a seismic state. What do we do about it? Well, in 2001, South Carolina implemented its own seismic design specifications. They were largely based on California and other seismic states that had developed their own. In fact, so much so that South Carolina had even copied some of the details from California that aren't actually used on South Carolina bridges, just because we wanted to make sure we had everything captured that may be necessary in a seismic design code. That was revised in 2008, with several revisions have been made since then to both improve the design as well as to make it more applicable for our state. So here begins the interactive portion of today's presentation. Just to ask by a show of hands, how many of you guys have performed seismic design on bridges before? So the presenters and just a few handful of folks. Okay, so I'm going to talk about some things that are typical to the seismic design of bridges in South Carolina and try to clarify where they're applicable in other states and other areas as well, based on different specifications. Of course, like Dr. Kowalski said, there'll be a question and answer period later if there's anything there, but we'll go through this relatively quickly. But basically, South Carolina, like some but not all other states, exclusively uses a displacement-based design where we calculate the displacement of the structure, and we use ductility to determine whether or not those displacements are satisfactory. So basically, we determine what sort of demand the structure actually undergoes, how far are the vents going to move in a seismic event, for instance. And we compare that to how far they move at, say, the point at which a plastic hinge forms. We also consider how far they can move. So at what point does the column or pier rotate so much that it can no longer accept load. So the principles behind this are that we have, as a state, chosen to limit ductile behavior to the substructure element and facilitate an essentially elastic superstructure. Now, Dr. Huff just talked about other strategies whereby maybe that's not always necessary, but in South Carolina, the design code and the design assumptions are based on that fundamental assumption. Also, our objective in this goal is to limit hinging to areas that can be inspected after a seismic event. So again, you've got an earthquake that happens, you want to be able to go out and see if a bridge is still going to be able to support load, performing adequately, what sort of repairs are necessary. You want to be able to see where the damage is. And so in doing so, we try to limit any sort of hinging to areas that can be inspected and repaired. One other thing that we have to consider in South Carolina is the impact of liquefaction. So liquefaction occurs when a seismic event causes the soil to lose its shear resistance, and essentially you get a much weaker response to the soil and you lose some of its capacity to resist load at certain locations throughout its depth. We make some assumptions about how that liquefaction is handled. These assumptions are not always consistent with reality in the sense that we know that there are variations for how liquefaction actually occurs in the substrate. But we have chosen the assumptions that we have to be conservative relative to what will happen. So one thing we have to do is we always have to consider a liquefied and a non-liquefied condition. So we assume that the structure has to resist the ground motion as if none of the soil loses its capacity to resist the load, and then assuming all the soil that can liquefy does indeed lose its capacity. We both assume that that happens at the onset of the seismic event, so immediately as soon as the load is imparted into the structure, and that all the strata liquefies at once. Those are not probably true, but like I just mentioned, we've chosen that to be conservative. Lee Marsh mentioned a minute ago about some of the reasons why some states, in particular South Carolina, evaluated the 2,500-year event. South Carolina does design its higher demand requirements against the 25-year event, so the safety evaluation earthquake that has a return estimate or a return period of 2,500 years. And this slide just kind of articulates some of what Lee Marsh mentioned a minute ago relative to the difference between a 500-year return event and a 2,500-year event for, say, South Carolina. Whereas, say, in California, there's not much difference between a 2,500-year event and a 500-year event. In South Carolina, it's the magnitude of, like you mentioned, approximately 6. So that's why we have two events that we designed for, and why we use the 2,500-year event for that safety evaluation earthquake. The FEE, the function evaluation earthquake, is the event that we try to make sure a structure, usually what we want it to do is be able to maintain traffic after the event. We want to make sure that it can still function as a bridge after maybe some minor repairs are needed. And like I mentioned on my slide up here, typically the SEE governs the size of elements, rebar configuration, maybe even governs the structure type itself. Whereas the FEE will typically, what we'll do is we'll try to make sure some of the elements that we need to remain elastic do so, and we'll make sure that we don't engage substructure elements when we don't need them in the FEE event. So, with regards to how we determine what sort of level of analysis is done in our bridges, we have to determine what sort of design category is appropriate for a particular bridge. So in South Carolina, we consider the combination of both the operational classification, so essentially how important is the structure to maintain, combined with the expected demand on that structure itself, and that gives us an operational classification relative to what level of detail or what level of analysis will be required. One thing interesting in South Carolina, of course, and every state I'm sure has their own OC requirements, but in addition to typical elements in the highest operational classification, such as structures that do not have detours and or long detour lengths, we also include some specific roads that are associated with earthquake evacuation routes. So once again, South Carolina is designed for those. So what does it mean if we have different design categories? Well, basically what we do is we consider what level of seismic effort is associated with each of these based on those design categories. In SDCA, we would look at making sure that the sheet widths are large enough, which, by the way, is always one of the most important elements of seismic design, is making sure that the path is large enough that when the seismic event occurs, the structure doesn't fall off. It's a big deal. You can't design it if it doesn't do that, or if it doesn't satisfy that requirement. And substructure to superstructure connection capacity. We start getting into some of the more technically difficult analytical modeling techniques at SDCD and above. Start adding multi-mode spectral analyses models. Consider displacement demands at SDCD, even though we can use a simplified procedure for determining some of the actual path. So as I showed a minute ago, we determine seismic performance of a bridge based on both the combination of the demand on the structure as well as the ductility of the structure. In SDCB, we do a fair amount of analytical modeling to determine the demand, but we can make some assumptions and some simplifications to get the actual path. Once we get to the SDCC, we actually have to use analytical modeling techniques to do both sides of that equation. And then at D, we also have to consider each frame on its own as opposed to allowing the entire structure. And here is just some of the definitions I mentioned before about relative locations of little forms, as well as some of the displacements. So, some elements that are unique to South Carolina and what we do in our design. The one place I'll start with is rebar. In South Carolina, we use exclusively A706 grade 60 rebar in all of our structures, in every part of all of our structures. That is, I don't know about unique, but certainly not common. I've spoke with other seismic engineers and other codes, and there are other options in many other places for rebar use. But in South Carolina, both between the better performance, or let's say the more well-defined performance of the rebar relative to yields and tensile stresses for the grade 60 A706 bars, we say, well, we'll use that not only in our seismic, hinge locations, for instance, but to make sure that we don't use it in the wrong part of the structure. A contractor doesn't grab the bar that's in the deck and put it in the column by accident. They say, you know what, we're going to eliminate all potential for human error. We're going to go ahead and use that same rebar in every part of the structure. It's relatively conservative, but we believe as a state that the conservatism is warranted and the cost doesn't rise so much that it causes a concern relative to the bar selection. Additionally, we require butt-welded hoops. That's different than some other places where you can use spirals. This is just a place where South Carolina is more comfortable with the butt-welded hoops. There's some philosophy that, if you use a spiral, part of the spiral may come undone and you don't know how the rest of the performance is going to be. I think there's been some discussion and research that's countered that. But again, South Carolina has its own requirements that it's stuck with on that. And one thing that the use of the A706 grade 60 rebar does do for South Carolina is, in comparison to what the guide spec allows for either the 615 or the 706, there is a lower requirement for overstrength modification that's required based on the So these are some of the strain properties, and what I've got up here is from the AASHTO guide spec, but it is very similar to what's done in South Carolina, except, of course, as you see there, that's the A706 bars that are used in South Carolina. We do have slightly different strength properties from the guide spec, but the strain requirements are nearly identical. And of course, as I mentioned before, we don't allow the use of A16 615 bars in the Rowan project. A few other elements. We do have differences between the confined and unconfined models of concrete. Figure as an ACI convention, you guys would be interested in that. We do try to use the Mander model for the confined concrete areas. And we do consider bilinearization and trilinearization of the moment curvature of reinforced columns. SCDOT has a little bit of a different approach from, say, California, where you would use an elastic and perfectly flat curve up here for California, whereas there's a slope to that curve in South Carolina. And this is the pre-stress concrete down here. All right, so a couple of examples I'm going to go through. This is the detailing from one of the bridges in South Carolina that was a strutted vent. Struts were necessary because vessel collision was a significant loading condition on this bridge. So this bridge had high wind loads and seismic demands and vessel collision on it. So yeah, lots of fun. But on this particular element, some of the challenges, in addition to rebar congestion, was making sure that we had enough steel in the columns to facilitate redistribution into the superstructure of some of that vessel collision load. Well, in doing so, that adds a lot of steel into the columns, and that increases the steel that's required for capacity protection of the cap and the shaft element. Additionally, we tried to force this element here to be essentially a rigid link where the column and the strut came together, so we added even additional steel in that area. And then, of course, capacity protection was required down in the high moment areas of the shaft. So a lot of ways that we had to account for the seismic demand on this particular structure. Awesome. And again, I didn't mention earlier, but capacity protection is essentially the objective whereby we make some elements stay elastic in a seismic event by increasing the demand that we impose on the design for those elements. So in this particular case, what we have to do is we have to take the actual loads associated with a seismic event for the yielding of this column, for instance. We increase it by 20% and we design the elements to stay elastic, that are designed to stay elastic against the demand imposed on that element by the column hinging. And we design so that we have enough steel in those elements. In some cases, enough size, but certainly enough steel to facilitate those elements staying elastic. Another interesting challenge that we had was we had a project where this is an end-bit cap, but we had a precast wall directly in front of this that we didn't want any soil loads imparted onto it from a seismic event. So what we did is we put two levels of casing around the end-bent shaft, which is what we had to use on this particular bridge, to isolate the interior shaft, which is actually where all the detailing of the concrete is, from that wall outside. So we actually put like a packing peanut in here to make sure that there would be no load imposed on that wall from the seismic motion of this abutment. So, as part of this presentation, I wanted to talk a little bit about not only South Carolina, but other seismic states, as well as places where seismic design is considered. So, this particular, and now a lot of information coming at you pretty fast up here, but just some things to think about. I selected these states just because I had access to both the information from them and resources within my company's network to be able to determine what sort of response I could expect in a seismic event in these places. Displacement-based design, for instance, in South Carolina is required as it is in California. It is allowed, of course, in Nevada. In Kentucky, for instance, it's used on bridges that require it, long, complex bridges. Force-based design is not allowed in South Carolina or California, permitted in Nevada, and is commonly used in Kentucky on conventional bridges. I mentioned before where South Carolina uses the ASTM 706 grade 60 bars. Again, to put that in perspective, California uses that primarily, but allows grade 80 bars in capacity-protected elements, straight bars in capacity-protected elements. Nevada uses those bars, the ASTM A706 grade 60 in substructure elements. It uses grade 75 in superstructure or non-yielding elements. In Kentucky, only uses the ASTM A706 grade 60 bars in plastic hinging. So, a variety of different approaches based on the state's preferences. In South Carolina, we typically don't have rectangular columns because the SDS doesn't clarify the detailing for those columns. California, it's pretty common to have rectangular columns. What you would do is you just have circular reinforcing inside of those rectangular columns. Very common in Nevada and not so common in Kentucky. They also prefer a rectangular round column. So lots of different approaches. to solve the same problem. A few limitations from South Carolina's perspective. First off, this SDS, South Carolina Seismic Design Specification, is only valid for concrete substructure elements. I know here at the ACI conference, everybody's cheering that. You know, concrete is our primary interest here, right? But there are steel substructure elements, and what you see on the lower left is actually a place where we've used steel piles as our primary substructure element. We had to work with the DOT to discuss meeting seismic requirements for that bridge. Same thing for pre-stressed piles. That is covered in the SDS, but it's very challenging to meet requirements from the SDS's ductility requirements, rather, for that substructure type. So we often have worked with the DOT as well to discuss options for variances from those requirements for pre-stressed pile. And I mentioned those problems. A few other limitations. As was mentioned earlier, yielding superstructure is a design strategy, but it's not one that's addressed in the SDS currently. And typically, larger cable stay, arch-type bridges, these are not covered by the SDS as well. If you have one of those bridge types, project-specific criteria are usually required. Often the SDOT will put out those criteria in advance, but obviously that will be a different type of analysis as opposed to what's typically done on this particular. A few places where further study is going to be investigated. South Carolina hazard maps are currently being updated. They were updated once before in preparation for the 2008 SDS publication to account for some of the local effects from South Carolina geology. They're being updated again. And this is where I'm going to have to defer to some of my more geotechnically inclined colleagues to give you some details with regards to that. But essentially what's happening is they're trying to find a way that you can do site-specific studies without relying on some of the BC boundary information. So again, I think that's very interesting, but it is not it's not something I can dive too deep into. I'm very interested to see what they come up with, though. One thing I'm working with right now on a bridge that I'm designing, like, this week, is the combination of both inertial and kinematic effects in liquefaction from an area. So, for instance, if I have a bridge where the abutment is going to experience liquefaction in a seismic event, well, the slope failure of that abutment could be restrained by the abutment itself. We can use the substructure elements to help restrain some of those effects. But in doing so, there's load imposed on the abutment. Well, do I need to consider, as a seismic engineer, the entire demand associated with a seismic event? So all the displacement from my seismic event to occur concurrently with the maximum liquefaction load in the substructure. South Carolina doesn't provide any guidance on that, and so we usually are pretty conservative relative to that assumption. But that is guidance that the SDS is lacking and we would love to see. And as mentioned before, some of the fundamental assumptions about liquefaction in general are not necessarily true. So the question is, do we try to reinvestigate some of those assumptions to improve the correlation between what we're assuming and what we believe is actually happening? All right, with that, got a lot of people to thank at HDR and several SCDOT colleagues who strangely didn't want to be named in my presentation, but I'll say Nick Harmon's name and Hong Fin Lee's name up here for you all, just to let you know how much I appreciate their efforts. And with that, thank you folks very much.